So this model is by Mack, not Walk, as I said before. Sorry about that. So we'll look at a two-level steady-state model with zonally symmetric basic state defined by U bar I in the which is in geostrophic balance with the geopotential. We will look at a two-level structure at 250 hectopascal and 750 hectopascal. Ui and Phi here are two layers which correspond to 250 and 750, as we will see in a minute. So the variables we are tracking are Ui, Vi and Phi, which are defined. This is a numerical model that's being solved here to test Charney's idea of an extratropical signal perturbing the tropics. So the perturbation vertical velocity in pressure coordinates dp dt is defined at 500 hectopascal. There is a static stability of the background state. Vertical velocity is set to 0 at the top and the bottom, as we will see as boundary conditions. Forcing of the tropics is applied at 40 north using a forcing function which is derived from observed mean longitudinal distribution of meridional velocity component. So you're in a zonally symmetric flow field, but there are meridional perturbations generated by, let's say, a breaking Rossby wave. Then you want to see how that signal can propagate into the tropics. That is derived from a real world. The zonally basic symmetric basic state with U bar 1 and U bar 2 is prescribed distribution of the perturbation kinetic energy in the upper troposphere and the lower troposphere are derived, and we look at the impact of the basic state on how far the perturbation kinetic energy travels towards lower latitudes. So there is the structure of the two-layer model. You have the upper layer centered on 250 hectopascal, 500 hectopascal is the mid-level of the atmosphere, 750 hectopascal is the lower layer with UN and U2 basic states prescribed. We are looking at perturbation in terms of U1, V1, Phi1. So the basic state potential is also prescribed. Those are the boundary conditions. The vertical velocities focused on here at 500 hectopascal. So that is the section on the sphere. The zonal basic symmetric state looks like this. So this is in latitude, so there is no variation in the longitudinal direction. So in the upper layer you have strong westerlies with weak easterlies in the middle. So you are going around the equator. So you have lower layer with weaker westerlies in the extratropics and stronger easterlies in the tropics. So you are looking at this prescribed basic state and compute the perturbation kinetic energy in this prescribed basic state with the given forcing in terms of meridional perturbation velocities. And you can see that because of these easterlies in the lower latitudes, if you look at the locations where the transition happens from the westerlies to easterlies, obviously in the strong westerlies there is a strong perturbation kinetic energy that is headed towards the lower latitudes, but hardly gets into the deep tropics or the equatorial region. In the upper layer, lower layer, the easterlies are stronger and broader, so the kinetic energy, perturbation kinetic energy, the signal that's traveling, is weaker and dies off a little bit quicker towards the lower latitudes. But if you change that and prescribe easterly symmetric basic state in both layers of -5 meter per second, then you can see that the perturbation kinetic energy dies off even faster because everywhere you have easterlies. If you prescribe a westerly symmetric state in both layers with westerlies of 5 meter per second, then you can see that the lower layer drops off quickly, but still makes it into the tropics and even has a little bit of a signal in the other hemisphere, whereas the upper layer does have a signal that's coming all the way into the deep tropics and crossing over into the other hemisphere. The main message is still the same. The westerlies, which means when we go into the real situation, the westerly duct that exists in the central Pacific and the central Atlantic can allow extratropical signals to penetrate into the tropics, which is important in this case because we are looking still for the baroclinic processes and whether they can be locally generated or they can also be triggered from the penetration of a perturbation from the extratropics. Okay, so these are basically results of two experiments with the steady state two-level model that we already saw: constant westerly zonally average basic state and constant easterly basic state. Obviously signs are switched again. Peter! Okay, so latitudinal distribution of perturbation energy at both levels are shown in the lower panels. I didn't include the model here, that's shown in Appendix J, but I wanted to just focus on the physics of it. So in the next podcast, we will look at equatorial wave propagation. Now, instead of a zonally symmetric basic state, we will have zonally varying basic state. Okay, so with the errors in the book and with the complications of the equations, I'm trying to wade through to just the physics and make sure that we keep the physics solid and follow the physics. Okay, we'll see detailed examples now, which will make it clearer.